It's my pleasure to introduce the speaker for the week, Professor Mike McAlpine, who is going to speak about 3D printing functional material and devices. Mike received his PhD in chemistry from Harvard and his bachelor in chemistry from Brown a few years back. We're very happy to have him with us. He's full professor in mechanical engineering and is the 3D printing guru / expert on campus. He has received numerous awards, including the PKs, including the Junior Investigator from NIH. So without further ado, Mike, the podium is yours.
Okay, thanks for having me speak here. Basically, so as Nikos mentioned, we are a 3D printing group here at the U. And the idea is to go beyond traditional hard plastic 3D printing and towards 3D printing of functional materials, which obviously doesn't have a very well-defined meaning to it. But in our minds, what it means is essentially electronic materials, biological materials, the merger of these two worlds together, bionics, for example. And in particular, one of the things we're interested in is semiconducting materials and devices and printing those. That's sort of the space where we have, the most significant IP and where we think the future lies with 3D printing. But of course, there's so many things you can do with this tool that you're not limited to any one particular material. And that's sort of the beauty of it, is that you can incorporate many different, whether it's the cells, whether it's the electronics, merge them all together on a single platform, which you can't really do right now, except, the clean room, traditional microfabrication facilities don't quite get you there. They involve harsh chemicals and unnatural environments for biology, and everything's limited to two-dimensional planar devices. And we want to sort of transcend all of that with this next generation of fabrication approaches. Okay, so this is a robotics colloquium, and we are in the mechanical engineering department, but we're not working on a robotics problem per se, which we're not trying to build robots, like these beautiful Boston Dynamics robots that behave more and more like humans. In some sense, you might think of this as the inverse problem, which is basically trying to take humans and make them more robot-like by integrating devices onto the body as seamlessly as possible in a three-dimensional format. And the classic example of this is something like a cochlear implant, which has been around for decades and essentially is a wire that's threaded through your cochlea. So it is actually two-dimensional in that sense and interwoven with the body, that basically can take someone who's completely lost the ability to hear and allow them to hear again by brushing up the electrodes against the nerve ending. So it is actually a bionic device that restores hearing for regenerative purposes, but it's not. I wouldn't necessarily say that the average person can go get one of these, if they want to expand the range of hearing and hear into the range of dogs or something like that, which you can actually do with these types of devices, because the surgery involved to implant this is fairly invasive. It comes with complications. And so the question is, can we take these devices that are used for regenerative purposes and, first of all, make them more seamless and easier to integrate on the body with minimal surgery and complications, but then maybe even give someone who doesn't have an impairment, augmented functionalities or capabilities beyond what biology ordinarily provides, and do it in a way that's, again, seamless and integrated on the body, and perhaps even something you could do at home and not have to go anywhere like a specialized facility to implant these devices. That's the idea. And if that sounds kind of far-fetched, then just look around you, because many people are wearing smartwatches, which is essentially the closest that the average person can get right now to being fully bionic, in the sense that, if I went 50 years ago and told someone that they can access any information that's ever been known by mankind just by a few taps on your wrist, of a device that's worn on the wrist, then I think that they would think that that was pretty absurd. And yet now it's so commonplace that we don't even think about it. But that's really what it is. Now, at the same time, it's not quite a seamless merger with the body. It's a brick that's really tethered to your wrist. And the reason for that is not necessarily because of the glass or the metal that you see in the picture there. It's really the underlying semiconductor that powers the entire device, which is a silicon wafer and a silicon chip, single crystal silicon, which has the advantages of being a material that has high electrical mobility, so it can operate quickly, 2 gigahertz processing, and has the other advantage that it's cheap and you can immediately process it into several billion transistors on a chip, which is amazing. But it has a disadvantage that it's a hard, rigid, and brittle material. If you drop it, it shatters. It has to be processed in the clean room. You have to crystallize the silicon at high temperatures. And so this means that it's not really a seamless interface with the body. You clearly know where your wrist ends and the watch begins. So the question is, can you make this truly a more integrated or seamless integration of the device on the body? So that means that you have to go beyond two-dimensional electronics, which pretty much all electronics is, into the third dimension. You have to be able to take the electronics and make it less brittle and rigid and make it more tissue-like and skin-like, soft and stretchable, and overcome those mechanical discrepancies. And then ideally, this would be something that can be done at room temperature, so it doesn't require high temperatures that may burn the skin. So we think that 3D printing is one potential avenue for doing this, but of course not the traditional 3D printers, which do amazing things, and the FDM type of style of 3D printing has roots in Minnesota. It was invented in Minnesota. And you see an example of that on the right-hand side, where you're able to essentially print this intricately designed plastic object on a printer by essentially taking filaments of polymer, feeding it through the printer, it melts it, extrudes it, and then it solidifies into a hard plastic that you build up layer by layer to form the type of structure that you see there. So it does require heating. You can get to the third dimension, but this is essentially a hard plastic, so it's not really conformal with the soft tissue of the body. And then finally, and most importantly, the plastic looks nice, but it doesn't have inherent advanced functionality to it. The hard plastic can be used for mechanical applications, but it can't really obviously be used to do the types of processing that is done in your smartwatch that you see on the left-hand side, the sort of higher order electronic semiconducting processing, which is one of the most amazing inventions by mankind to date. So we need to sort of take this concept, but then take it to the next level and build new 3D printers that can start to address those types of challenges and overcome these discrepancies. And that's what we do in our lab, because we are mechanical engineers, so we know how to build stuff. And so this is what our printer looks like. And in some sense, it's similar to the one that you saw before, in the sense that it moves in three-dimensional space, and then it extrudes inks onto a platform. So instead of extruding melted plastic, you essentially have inks loaded into these syringes, and at room temperature, you're just extruding the inks using pneumatic air pressure and air dispensing. And that's what you see with the dispensing system on the right-hand side. The air flows through the tubing there, pushes the ink out of the nozzle onto the platform, which is moving in 3D space. And then, if you then wanted to apply heat for sintering or apply UV for curing, you can do that. But on the single platform here, you can load one syringe with cells, load another syringe with nanoparticles or some other electronic material, load another syringe with supporting silicone, load another syringe with something else, and just keep doing that. And essentially on this single automated platform, you're able to, in some sense, take all of engineering and material science and sort of condense it down into any type of 3D object that you want, having any type of functionality you want woven throughout that object, or even print directly on the skin to, print your next smartwatch, tattoo your next smartwatch directly on the skin. So, and then in addition to that, the most important component of this printer, in my opinion, or what I've come to realize, is the thing that's not shown in the image, which is on the right-hand side. which is the computer that controls everything, because that's the brains. And you guys know more about than I do, because you probably know some artificial intelligence or machine learning, and having the computer become intelligent and have advanced controls here. We have Professor Rajamani involved, who in this colloquium today, who is an expert on that, much more than we are, means that you can start to give the printer a set of eyes, a set of brains, real-time feedback, and then maybe have it be part of a larger robotic system, where the printer is just one thing that the robot does, but then the robot can do many other things. Like the robot can be a Da Vinci robot that does surgery, but then part of it is another arm that prints the biomedical device at the side of the surgery, and then another arm does something else, that sort of thing. So I think there's tremendous potential here in the robotic space, in the material space, the bio space. And I think people must agree, because these things are spreading like wildfire, whereas 10 years ago, I'd never heard of 3D printer, even though this has been around since the 80s and 90s. So you may be asking, what kind of resolution can we print? And that's shown by this middle image here, which basically is, how well can you force material through a nozzle? What size is the nozzle? And really that's going to be limited to about 10 to 100 microns at the lowest end. It's really difficult to have a nanometer sized nozzle that you can force material through without clogging or breaking. So typically we stick to the 10 to 100 micron resolution range of the actual printing process itself. So we call this microscale printing, but the ink itself can actually go down to the nanoscale. You can have, functional quantum dots or metal particles. That's where we get our semiconducting functionality from. So the ink can be at the nanoscale, and then you print at the microscale. And then finally, like with any 3D printer, you can build up devices that are large, foot by foot by foot devices on the platform. And so those are macroscale devices. So essentially you're traversing the entire length scale from nano to micro to macro, in addition to being able to incorporate many different types of functionality into the printer. So we call this both multi-scale and multifunctional manufacturing process. Okay. Do you guys do questions at the end, I assume, or questions throughout? Probably at the end. Well, we'll just take them at the end. So here's an example of our ability to print a type of ink, which is a composite between silver particles and silicone. And so silicone itself is actually difficult to print on a conventional printer because it's a thermoset rather than the thermoplastic. So it doesn't really melt the way a plastic does. So that by itself is difficult. But then what we can do here is mix into that silicone precursor ink some silver particles, which makes it not only a stretchable material, but also electrically conductive as well by having silver mixed in it. You can sort of see that with the color here. It's not clear and transparent like traditional silicone. It has that sort of gray color to it. And from there, this is what it looks like with the particles mixed into that ink. So it's almost like a fabric that you're printing here that's electrically conductive, that's entirely 3D printed, but also stretchable as well. And that means it can function as sensors depending on how much of the silver you load into the ink. If you load too much silver, then it's highly conductive. If you load not enough silver, it's not very conductive at all because the silver particles don't touch one another. And if you can meet the thresholds called the percolation limit, that's sort of halfway between those two zones, then you have a highly sensitive region where the particles are initially separated, and then as you compress them together, then they form a conducting pathway. And therefore you have a high change in resistance that can be used as sensitive sensing platform using this 3D printed composite ink. Okay. And then from there, you can build more complex devices from that, where the sensing layer actually forms the basis of this coil here, which gets compressed. But then you can have top electrodes and bottom electrodes, which are more conductive. And then you can have other types of supporting layers to keep the structure in place as you print it, and then remove it at the end to form a freestanding sensing type of structure like you see here, all basically performed on the same 3D printing platform where you have the multiple inks loaded into the different syringes and nozzles, and they integrate with one another and coordinate among one another in order to print this final device that you see there. And so we'll show that in the actual video. So as you can see, we can even do this on different types of surfaces. This is a model hand that you see there. And the hand actually has, the finger has a little bit of curvature to it. And so we actually did a 3D scan beforehand, and the device itself has some slight curvature as well to compensate for that. But you can see we're coordinating among these different nozzles, printing the different inks there to build the structure up layer by layer, all the different layers of this device. And then the sacrificial ink that gets washed away at the end, that's just used to support the top electrode, which is coming down here. And there you have a 3D printed sensor directly printed on this model platform, consisting of this composite silver silicone ink. Okay. And you can take it off the platform and then put it on your own wrist if you want, put it on a human wrist. And it's sensitive enough that it can measure the pulse, as you can see here. And then if my postdoc who did this work goes out, starts running, you can see the amplitude and frequency increase from the higher pulse rate of the with this next to the sensor. And you can easily scale this up to larger dimensions and more devices like you see here. So this is a 5, instead of being a single device like you saw before, you can create a 5x5 array of 25 of these piezo-resistive sensors, so that if you push this glass triangle into the sensing bed, then it'll map out those pressure deformations in the pressure map that you see on the right-hand side. Okay. Now, we were excited by that, but I, encouraged my student to see if we can go beyond a model hand into an actual, his biological hand, which is obviously more complicated. And this starts to get to this question of, can you directly print your next smartwatch on the skin, or directly tattoo your next smartwatch on the skin? So think of it as going to a tattoo parlor where the ink is replaced by electronic ink, and the tattoo artist is replaced by a robot, essentially. And the key thing here really is, there's obviously a number of challenges here, but the key one is that if you put your hand under the printer and this syringe is coming at you automated in an automated fashion, your hand is going to naturally move, whether you're shaking or whether you want to pull your hand away or whatever it is. You need to have cameras mounted on the printer to track that motion and compensate for it, so that you can essentially directly print this device on the back of the hand. In addition to that, we also do a 3D scan, so we understand the topology of the back of the hand beforehand. And then finally, the ink that we print is a silver ink, just like you saw on the previous slide, but this one is slightly different, where we use a different polymer that dries fairly quickly at room temperature, and therefore it's a conductive silver ink without requiring any type of high temperature curing, because the last thing you want to do when you print this silver ink on your hand is to have to sinter it or heat it or dry it or something like that, that may damage your skin or hurt your hand in some way. So it needs to be a fast drying yet conductive ink, and that was a tricky thing to work out. So as you can see, in this single problem here, coming together, you have the bionics aspect, you have the robotics aspect, you have the materials aspect, and you have the biological aspect in this integrated project. And these are the types of projects we like to work on. We find them interesting because they're sort of outside the box of how you might normally think, or what's being done really out there today. But believe it or not, it does work. And another way to think about this from an AI standpoint, which we're definitely not machine learning or AI people, but we got our feet wet a little bit, and we worked with a professor in the computer science department on this project as well, which is what you do is, by having a camera mounted on the printer, the camera is watching the workspace in real time. So the printing is happening, and then the camera is watching that. And so essentially what you have here is a closed feedback loop. So it's not the traditional scan and then print that you would find with traditional 3D printing, which is an open loop process. This is closing the loop. And that sort of brings up a tantalizing concepts of, well, then you can start to incorporate artificial intelligence into this. So you're sensing and adapting to the printing state, but then maybe in the future, which we haven't done yet, but we're interested in, maybe you can predict the printing state as you're as you're doing this to essentially speed up the process or make it more seamless or be less harmful to the body or less likely that the syringe might, penetrate the skin or whatever it is. So we're interested in this concept here of closing the loop with these embedded cameras and sensors on the printer, rather than the traditional open loop printing, but then maybe even in the future incorporating prediction and advanced AI into this process. And so we're highly interested in working with some AI folks, and there's lots of amazing ones on campus here to take this really to the next level, because we're really at a preliminary stage right now, and there's many things we could do here. So let's expand upon the ink a little bit. It's a silver ink again. It's in a polymer, and it's in a ethanol water solvent, and so it does actually dry within a few minutes at room temperature. And you can get basically within 2 orders of magnitude of bulk silver from this ink. And as you can see here, part of the magic of that happening is that there's silver flakes here, and the printing process actually shear aligns them so that they overlap with one another. And therefore, you have a nice overlap of the silver, creating a conducting pathway so that you don't have to do that additional sintering step, which would obviously damage the hand, be it temperatures that are too high. So this is what it looks like. Again, here's a movie in real time. So now that's a real hand instead of a model hand under the printer. We are using the printer there in a vacuum mode to pick up and place a light emitting diode LED on the back of the hand. And we're placing these tracking markers on the back of the hand, which allows us to track the motion of the hand. And then we do a 3D scan that gives us the topology of the hand, so we know what it looks like. Essentially, it's a rigid body in this particular case. And there's the silver ink that we're printing, and we're forming an antenna that connects to the LED. And this movie is sped up, but the hand, as you can see, is moving, and it's moving in completely random orientations during this process. It's not, some type of periodic predictable motion. It's just random. But the printer is following those tracking markers and compensating for those, so that you can essentially deposit these various inks directly on the back of the hand to print an electronic circuit that connects to the LED that we placed in that first step there. And the interesting thing about this is that the printer that we're using here is not the large one that I showed before that we have in our lab, but this is a smaller one called a Delta robot, which costs about $400 and is lightweight. I can pick it up with one arm. So here, after you print that antenna, you can see you can wirelessly power the LED. So you can imagine, taking this Delta robot, putting it in your backpack, carrying it around with you, and then printing any type of device you want anywhere on the fly. Okay. You can remove the device if you want. It's only adhered really by van der Waals. So if you just peel it off, it'll come off. Or if you apply water to it, eventually it'll sort of wash away. So, I mean, it's definitely not a permanent device, but it does maintain its integrity for the most part over a period of a few hours that you might wear it. But obviously it doesn't last forever. Okay, so I thought that was exciting work that my student did when he showed me that. And then he came up with an idea, which I think is even more interesting, which is, which he was a really impressive student, like many of the students we have here at the U, which is this idea that you see on the left. This is sort of a traditional mechanics problem, which is the hand, while that's interesting, the hand has 6 degrees of freedom, because essentially, as I said before, it's a rigid body. And so therefore, it has 3 spatial degrees of freedom, X, Y, and Z. And then in addition to that, it has 3 rotational degrees of freedom, which is roll, pitch, and yaw. So that's 6 total. But the hand itself is not really changing its shape, right? And when you change the shape, there's a change in potential energy associated with that, and that's called a deformation. So a good example is, let's say instead of printing on a rigid hand, you wanted to print on the surface of a breathing lung or a beating heart or something like that. Well, that's undergoing expansion and contraction, which is a type of deformation. And so you need to be able to track those types of motions, which have higher order degrees of freedom, and maybe potentially even infinite degrees of freedom, depending on how granular you want to get. But of course, that increases the computational complexity quite substantially. So, can you reduce the problem down to a simpler problem where you only need a few tracking markers and are able to do this? Okay, so the trick here is that we actually separate this into two phases. We do actually do a set of pre-scans beforehand to try to reduce the complexity of the problem and essentially build a reduced model so that we'd only need a few tracking markers in real time to track the deformation. But once we figured that aspect out, that you can see we had, first we started with a membrane that we pump air through. So the membrane is expanding and contracting. You can see the printer is moving up and down as it tracks that motion and is able to essentially fill in the membrane with this smiley face based on various colored silicone inks that you see there. And then we took that over to an explanted lung like you see here. So now the lung is breathing and we're watching that motion and printing this sort of strange looking material that you see here. It looks kind of watery, but it's not actually. It's a mix of a polymer and water called a hydrogel. And we're printing that on the surface of the lung tissue here, again, with the printer watching those motions, those deformations there, and able to essentially print this device on the surface of the lung without ever puncturing the lung. You never see the needle there puncturing the lung. Okay, so what is that stuff that we're printing? I mentioned it's a hydrogel, which you may or may not have heard of before, but it's more than that actually, because mixed into the hydrogel are ions, lithium chloride. We mix into it, so into the water part of the hydrogel. So therefore, not only is it a soft, stretchable material, it's also ionically conductive as well, because the ions can move throughout the hydrogel and essentially conduct. So believe it or not, that transparent blob that you see on the right-hand side is actually a type of electronics. Believe it or not, it doesn't look like it, but it is. And of course, you have to cure it first, but once you do, you essentially are creating this ionic hydrogel-based device. So you cure that ionic hydrogel under UV, and then what you do is you place some electrodes around the circumference of that ionic hydrogel, and this creates a type of device called electrical impedance tomography device. And so essentially what you're doing there is, even though it's a uniform material, uniform ionic hydrogel, by placing electrodes around the circumference, you're and sourcing current and measuring the voltage continuously around the circumference, you are actually creating a pseudo imaginary set of array of sensors on the device, even though you're not actually dividing the device into arrays of sensors, but creating that circumference of electrodes creates a pseudo array of sensors on the device. And that's the beauty of the tomography system. So that now when the lung is breathing, after you created this device, not only were you able to print it on this deformable surface, but it now can actually map the deformations after the fact. And so therefore, maybe this can be used to do something like interrogate the respiratory state or state of respiratory distress in a COVID patient. Okay. So that shows that we're able to print various types of materials, including polymers, soft polymers, beyond the hard plastics. Also, two types of electronic materials. You saw the silver-based electronics, which is electrically conductive, and the ionically based conductive device. But what the world is built around is not conductors. The world is built around semiconductors. Conductors transmit information, but semiconductors process information, right? And we know how valuable the semiconductors are because of the semiconductor chip shortage that's currently happening due to the supply chain issues. And that means we can't get chips into cars, we can't get chips into your phones, chips into laptops, and the chips are really where the intelligence lies in the computer. Okay, in the semiconductor. So we found that very few people are really pushing into the 3D printing semiconducting space, despite the importance of semiconductors and despite what people have done in other types of printing spaces, such as the inkjet printing space, where they have actually created arrays of solar cells, photodiodes, transistors using inkjet printing. So we wanted to start to incorporate semiconductors into the 3D printing space. And luckily for us, since no one had done it yet, we were able to get a major patent on that. Although at the same time, I do think it would be nice now that we sort of set this foundation if more and more people got into this, and I think people will because of how important semiconductors are. so we started with the question of, well, can we actually fully 3D print an LED? And I mentioned before that many people are inkjet printing these types of devices, but even in the inkjet printing papers, if you look at them closely, they all involve, at least at some step, an instrument in the microfab facility, whether it's the spin coater, whether it's the metal deposition. Usually there's at least one step in that process in tandem with the inkjet printing that involves a traditional microfabrication facility. And it pains me to say it a little bit because, we have one of the best microfab facilities in the world here on campus with the Minnesota Nano Center. But at the same time, we're not using it because what we're trying to do is take all of that instrumentation and essentially condense it down to our 3D printer and do everything on the printer and never have to enter the clean room, so that eventually you can put this in the hands of the average person and they're at home and they don't have to go into the clean room themselves. They can just print a semiconducting device at home. That's the idea. And so because of that restriction that we're placing on ourselves, it does mean the device is a little bit complicated. You have to incorporate various types of materials into the printer, but the printer can handle it. So typically we use silver nanoparticle ink as our bottom electrode, and then we use 2 types of polymer conductors for hole transport, and then a quantum dot layer for, this is an LED, so that's for the light emission layer. And the top electrode has always been a little bit tricky because you need to have another contact, but if it's a metal, then you'd end up having to sinter it. Like if it was silver nanoparticles, you would have to sinter it, which would damage all the layers underneath. So what we do is we 3D print this liquid metal called gallium indium, which is a field that was essentially discovered by Michael Dickey, who was a professor at North Carolina State University when he was a grad student. So this liquid metal is just like a blob of liquid metal that you deposit on top, and then you don't have to sinter it. It basically forms your top contact, although admittedly it is a bit messy and there's probably got to be a better solution out there for that, but it's a good starting point. Okay. So the trick here is, how do you actually 3D print a semiconductor? So what we use semiconductor quantum dots. So these are small particles of semiconductors. So that solves the problem where we're not using a large single crystal. So therefore you can create an ink. But even then, when you deposit this ink of semiconducting particles, you can see that you don't get a nice uniform distribution of the particles. And if you're trying to make a large scale array of devices, you want to have good uniform device properties and device performance. And you're not going to get it with what you just saw just there, which is the well-known coffee ring effect. Happens when coffee dries. The particles essentially, instead of being uniformly drying, they actually form a ring. And that can lead to pinholes and other types of defects in the device. And so it's undesirable. So the trick here is, well, if you can mix in a co-solvent, so it's an old chemistry trick. You have a co-solvent which has a lower surface tension. You mix that in. So instead of having pure toluene, you actually have a mixture of 2 solvents. Then this magical thing happens where you have this effect called the Marangoni effect, and it counteracts the coffee ring effect. And now suddenly the drying process is substantially more uniform, and you get this nice uniform distribution of particles throughout the droplet. I mean, still obviously not perfect, but much better than it was in the first video. And that allows us to get better device yield and device performance. Okay. So that allowed us to fully 3D print, as we call it. We call it fully 3D printing different types of LEDs. This is a green LED. This is an orange LED. Again, all the materials came out of our single printer, and even the LED material itself, they're both cad selenide quantum dots, and cadmium selenide, the band gap changes as you make the particles smaller. So the single material can actually give you 2 different colors depending on the size of the particles, whether it's green or orange. If you want to know more about that, you can take my class, Introduction to Nanotechnology. We talk about that. But so the color purity is good, and the color saturation is also good. And but I mean, obviously it's not a world record, but it's, given the fact that it's entirely 3D printed on our single platform, it's a good first step. Now, actually, we did that before we moved to University of Minnesota. Then when we moved here, we found out that Professor Kortshagen synthesizes these silicon nanocrystals using a plasma system. And now we can actually start to incorporate silicon into our 3D printing system. So silicon, as you know, is the mainstay of the semiconductor industry. That's why it's called Silicon Valley. So now we can actually introduce silicon into our 3D printer and have the world's first fully 3D printed silicon-based semiconducting device. And the beauty of these quantum dots is the fact that they are actually 5 nanometers and smaller, which what happens with silicon is at that length scale, 5 nanometers, silicon behaves more like a quantum material than it does a bulk material. So it does something which bulk silicon doesn't do, which is it emits light. So a wafer of silicon will not emit light. That's why you can't really put optics on your electrical chip, because silicon doesn't emit light in the bulk state, but these silicon particles do. So we can actually create an LED here based on these silicon particles. As you can see, it glows red. So that's red emission, band gap emission, essentially from these silicon quantum dots that were given to us, and building up the same type of device that you saw before. Okay. Now, if you've ever worked in the clean room before, you know it's all two-dimensional, right? It's all wafers, flat wafers. It's all, you know, your laptop is flat, your cell phone is flat, smartwatch is flat. All electronics are flat and rigid and two-dimensional. And you can do layers, of course, a few thin layers of structures, but you can't really build truly three-dimensional electronics using the conventional microfab approach. But with the 3D printing approach, you can easily just start building devices into the third dimension and have three-dimensional circuits, right? So that was the idea here is, we have all these different colors of LEDs. Well, we can just print them all in a 3D space. It's almost like a Christmas tree of LEDs here. And, embed it all within a cube of silicone, which is also 3D printed, and have, probe different points of this cube here and have different LEDs light up and have different colors emitting from the cube. And the real cube doesn't look quite as beautiful as the drawing on the left, but it looks okay. And so what you can see here is that there's silicone that we're 3D printed, and then you can actually see these blobs of the liquid metal on the top there. And then you have the quantum dots in there. You have these electrodes, which are also 3D printed coming out the side. This entire structure here is 3D printed. And as you probe different regions of the cube, you can see you have either orange emission or green emission from the cube, depending on where you're probing it, and have different colors coming out of this cube. So this is a truly three-dimensional active electronic architecture, which again, the cube is 1.5 centimeters on the side. So it's a macro scale object, but the printing can be done down to the micro scale, and then the quantum dots are nanoscale. So the cube itself is sort of multi-scale and multifunctional, embedded within this object here. So that was that was some of the first work we did in that area, but more recently we started to print not just LEDs but also photodiodes. Photodiodes are they're not light emitters, they're light receivers. Okay, and now we can actually print them directly on various types of surfaces. So this is the convex surface of a glass hemisphere. And so the first layer we're printing there are these silver nanoparticle inks, and we're printing it up the side of the hemisphere. And each ring that you see there is a position where light can come in and trigger the device. So it's a pixel in this photodiode array. And we probably have, I don't know, 15 or 16 pixels in this entire device. So this is the second layer. This is just a polymer layer for hold and electron transport. And then this is the semiconductor layer. So in this case, the semiconductor is not a quantum dot. It's actually a polymer blend that you see here. So, various different types of materials. And then here's that sort of blobby liquid metal top contact that we put there that finishes off the device and creates the other electrode. So now you have a photodetector array that's directly printed in a hemisphere that looks sort of like an eye, right? So it's a light sensitive device that shaped like an eye. Eventually it would be nice if we can implant this against the retina and have a 3D device like that. So we call this obviously our 3D printed bionic eye. And each one of these circles again that's the light receiver part. So that's the pixel. Nowhere near, of course, the number of pixels in your eye or the number of pixels on a display or anything like that. But a good starting point. And actually, the devices are pretty decent in terms of performance. Again, we don't use any microfab processing here. So, and we're still able to get maybe about 20% external quantum efficiency from this device, which means that it's competitive with some of the lower end spin-coated devices that have been made, but not a world record, but still much better than people expected when we said we're going to put all of the electronics into the printer. So pretty decent performance is the point here. And as you shine a cross on the eye, you can see the cross is like the light of cross is overlaying these pixels. So those are the pixels that indicate that they're lighting up there when you probe them electrically. And what we're doing now is trying to go beyond the small scale few pixel limit to much larger pixel arrays. And this requires, as you might imagine, better control over the drying of the inks, to being able to print over large areas, being able to print condensed devices. And actually we have a paper coming out in January, which now shows that we can get up to 64 pixels. So basically an 8x8 array. But for now, I'll show you this, which is still the integration of multiple different types of functionalities on a single 3D printing platform. So the first thing we're doing here is printing a mirror on a glass slide. Okay, so that's a silver nanoparticle ink. And we flip that over, and we have these 4 devices there that are integrated together. The outer 3 devices are going to be LEDs, and the inner device is going to be a photodiode. So the LEDs are going to emit light, and the light is going to bounce off the mirror on the back and then bounce into the photodiode in the center, which is that device right there. So essentially, you're creating an integrated array of semiconductor devices that's fully 3D printed on a single platform here. And you can see each of the layers here that's printed, all the interconnects, some insulation. This is the top liquid metal again, that sort of blobby material. Believe it or not, you can actually write electrodes over that liquid metal, as you see here. So you can still connect electrodes to the liquid metal. You just write over it. And so I was surprised when I saw that the first time. But you have a fully integrated device here without ever having to go into the clean room. So on the right-hand movie here, and this is the last thing we're going to show here, but those are the 3 LEDs that are blinking. And again, that light bounces off the mirror that we printed and then bounces into the photodiode, so that the photodiode itself, so here's the 3 LEDs, 1, 2, 3, the photodiode's in the center. And so the photodiode is reading that light, receiving that light every time it bounces off the mirror. So you have the 3 LEDs turning on and off, and the photodiode is receiving that light and responding in the same way to that input of photons to the device. Okay, so is it the most beautiful device you've ever seen? Probably not, but it's entirely 3D printed. And I think this brings us toward a future scenario where the average person at home doesn't need to go out and buy electronics. They can essentially print any type of biomedical device they want, or device on a 3D printer, and takes us beyond the 2-dimensional limits of conventional electronics. And maybe we can think about starting to embed different types of active electronic and other devices within complex 3D biomedical systems or soft devices, which would be very challenging, if not impossible, to do with conventional microfab approaches, right? So we'll never get to 1 billion transistors on a chip like Intel. I fully admit that, but there's other niche applications, especially in the wearable space, I think, that we can target by being able to print on any type of surface and embed these devices pretty much anywhere. Okay, so that's my presentation, and hopefully you have some questions along the way, and I'm happy to address any questions you have. And this is just sort of a piece of the larger puzzle of what we can do, including printing cells, which I didn't even get to, on the same platform. So these semiconductor devices are printed on the exact same printing platform that we use to print cells for other types of projects. So it's such an amazing and versatile platform.
Great work, Mike. So
thank you. It looks like we have a chat question, actually.
It was a comment.
Oh yeah.
About
so I've read these. I've read these articles about people worried about microchips in vaccines and stuff, right? So non-existent. So are you worried about proposing to actually implant microchips into another? Well, I mean, basically, yes. I mean, so which, is it really a big step up now from wearing a smartwatch at this point? I think if we had said this maybe 10, 20 years ago, the fear factor would definitely be there, but I think now it's almost commonplace. Now, we're not really doing microchips, as I mentioned. I mean, our devices aren't smart enough to be microchips yet. We only have maybe 64 devices versus a billion, which so we don't have that level of intelligence yet. But I think for some initial applications, the light emission and receiving is a good one, because that's not really intelligence per se. That's more, you can use that for measuring your pulse or monitoring your pulse or whatever, or doing optogenetic studies and implantable devices and that sort of thing. So I think we're far away from being able to print a truly intelligent microchip into or on someone's body. I think for now, I think a near-term goal is, one of my dreams is, like, let's say you're in a car accident and right now you have to wait for the ambulance to show up, and you have to then get in the ambulance, be taken to the hospital, and then finally receive treatment. But if you have a printer in the trunk of your car, you can take it out of the trunk of your car and print a biomedical device directly on your body. So that to me is a more pressing issue right now than, the future one, which will definitely happen, which you're referring to, which is the start to incorporating intelligence into the body as well. So.
I've got a question, Professor McAlpine. Do you have any intuition or estimation of what the limit of this kind of technology is? Like, I know you've got 64 devices now. You went from 15 to 64. Is there, based on just the physics of what you're doing, do you have a limit?
Yeah, that's actually an excellent question. Because the question, it's a great question, because you always want to ask yourself, are you limited by the laws of physics, or are you limited by, as an engineering problem? So of course, this gets to the typical question, which is we're writing the electronics, unlike conventional photolithography, which has the advantage that you're essentially, with a flash of light, you can create 1 billion transistors in a flash, but we're writing it. So it's slower, obviously, as a manufacturing platform. But if you had a room full of nozzles, then you could essentially write them all in parallel. Or you don't even need, separate printers. You can have like a single nozzle that connects to a larger set of nozzles and basically move that around. But I think realistically, since transistors right now are on the order of whatever, 20 nanometers or some ridiculous number, and we're sort of at a length scale that's basically 100 or 1,000 times higher than that. That's really the limitation, is we can't really get those small scale features out of the nozzle. But at the same time, again, I don't think you necessarily need 1 billion transistors if you're trying to make a simpler biomedical device that maybe has a lower level of computation to it. So it is an engineering problem, but I think it's probably more an engineering problem than a fundamental physics problem, because people have actually proposed some creative ways to try to think about ways that you could actually get down to, let's say, the sub 1 micron or sub 100 nanometer scale using 3D printing, but we're definitely not there yet.
Thank you. Yeah, I would definitely accept my heart rate monitor being able to actually accurately measure my heart rate all the time. So,
yeah.
Other questions? So I have one, Mike. Where do you see the limit for this stuff? I mean, I'm thinking of pumps, I'm thinking of insulin pumps, of monitoring systems, but where, if I can ask, what will be the intractable or something that is extremely difficult?
Yeah, that's a good question.
Is there something, for example, when you are in your PhD that you thought that you could do, that you cannot do, or something that there are constraints or impediments that are extremely challenging?
Well, I think this entire field is extremely challenging. I mean, because we are actually integrating multiple types of materials and robotics on a single platform. I think the question is, and it's actually not just a question for our type of 3D printing, but it's a question for 3D printing more broadly, which is where are the applications, right? And this is not just a question for this particular type of platform. It's a question that even the plastics printing people need to address. And then not only where are the money-making applications, but then, you know, everyone, including my parents now, own smartwatches and cell phones. So the question is, what would attract them to go out and buy a 3D printer? You know, these are the sorts of things we think about as well. But you'd be surprised because we do actually have several collaborations with the medical school here on wearable devices, let's say for monitoring UV from the sun in certain types of wearable devices. So they do find this valuable. I think one other area of low-hanging fruit, of course, is to incorporate these types of systems into soft organ models, which may be used as surgical practice or surgical tools in advance of the surgery itself. So we've actually incorporated sensors and stuff into these models so that when you do the surgical practice, it gives you real-time feedback. But from there, you know, what's going to stimulate the average person at home to go out and buy one of these printers? I do think actually in the future, this will be the application. I think that if the average person could just print their next smartwatch, you know, directly on their body or print it anywhere on clothing or whatnot, and never have to go out and buy rigid electronics, I do think that that represents a compelling future in addition to printing biomedical devices at home. So in some sense, maybe it's not about making money, maybe it's about more the democratization of these types of technologies into the hands of the average person.
And I don't know, I will argue about the issue of money. I mean, there is a pretty well-known additive manufacturing player in town. When they came to me and they asked me about their idea, I told them, you have no market. So now they're a $2 billion company. So sometimes the markets are created as long as there is a need, you see, or people see this as something useful.
Yeah, I mean, I hope that that's the
other
case.
thing which I think, I don't know if there is any study of this market, but there is a growing number of people who are working X, and they are playing with new IP in their garages or in their basements all the time, especially with the COVID situation. So having the ability, and let's suppose that these guys have $2,000 to build a prototype, giving them a tool that will enable them to do this within this budget, I think is critical. And we're talking also not only the US, but about developing or developed markets.
Yeah, that's a great point. I thought of one other application actually too, which is we also have a technique for printing microfluidic channels as well, which we are actually working with a company on. But you're absolutely right. You're right. I mean, we shouldn't think of the prototyping space as a non-commercial space, right? The prototyping space is still a space where money can be made, right? So,
is this the company about the medical applications, the microfluidic cancer?
Actually, no. This is a company working with Steve Kester. The company's called GRIP.
I have something else in mind, but that's a great example of something that it came. The one I have in mind is actually if they are not able to do this, the microfluidic thing, they won't be able to succeed. So, and it's a very specialized fabrication. So, but right now it's prohibitively expensive if you have $10,000 in cash to start the company.
Can't pay for the clean room.
That's my point. So I think there is a niche area here. The thing is, I don't know what is the size.
Yeah, that's a good point. I don't know the answer to that either. So, but I think, you know, one of the things about that microfluidics project is that's printing microchannels, but we're printing the microchannels on Steve Kester's sensors, which are microfabricated. So I think we don't necessarily need to, although in our research, we're pushing toward, you know, getting out of the clean room as an intermediate step. You can imagine devices like that, which are partly microfabricated and then partly have 3D printed components on them as well, like microchannels on a microfabricated sensor, like sort of a midway intermediate point, right?
Thank you. Any other questions?
Yeah, actually, it's kind of related, not to bring it all the way back to the deep sciencey stuff, but is there something about the silicon, like the 5 nanometer flake structure, that stops you from 3D printing a non-planar shape and then 3D printing some photolithography material on top of it and masking it up and then flashing it with UV and then having what is essentially a wrapped 2D semiconductor device? I guess that's good.
Yeah,
that's the question.
So those are the type of ideas that people have sort of come up with for. In some sense, it's actually the analog of what Intel does when they do their multi-step lithography. And actually, there was another idea that someone threw at us once, which is similar to that, which is you saw that coffee ring effect. Well, what if instead of trying to eliminate the coffee ring effect, what if you actually use that to your advantage by having like small clusters of particles that form thin lines that are smaller than the diameter of the nozzle, you know, after drying, right? So you're printing at a larger scale, but then it dries into a smaller scale structure, you know, so that's a type of 4D printing, right? It's a time dynamic, which may lead to smaller structures like that too. So I don't know, I mean, the nice thing about this is lots of people are building this tool now, and that means that all this creativity is going into this, and you see all these amazing papers coming out. And so I think the creative ideas like that one would certainly be something that someone could do at some point for sure.
So thank you again. And just a quick announcement to all the participants in this class. Since you know the requirement, you cannot have more than 2 missing reports. We will be accepting reports till next Friday, the 17th, midnight. There are a few people that make me very nervous. They are missing reports. So again, please try to submit your report so we are basically on time, so we can release the grades on time. Have the best holidays. Stay safe and well. The same goes to Mike and all your families. And we will see you all in 2022.
Thank you. Likewise.
Thanks. Yep.
Thanks a lot.
Bye, everybody.